Intergranular corrosion, an overview. Lecture by Dr.G.Subramanian, Chief Scientist Retired, CSIR Central Electrochemical Research Institute. The coming 3 slides explains this behavior, intergranular corrosion, in a lucid manner, in a simple manner. Intergranular corrosion is localized attack along the grain boundaries or immediately adjacent to the grain boundaries, while the bulk of the grains remain largely unaffected. The figure on the right side top shows you the white colored patches along the grain boundaries shows the corrosion along the grain boundaries. This form of corrosion is usually associated with chemical segregation effects, like impurities have a tendency to be enriched at the grain boundaries. Otherwise, specific phases precipitated on the grain boundaries. Such precipitation can produce zones of reduced corrosion resistance in the immediate vicinity. Example of intergranular corrosion: sensitization of stainless steels. Heating up of austenitic stainless steel causes chromium carbide to form in the grains. Chromium is therefore depleted near the grain boundaries, causing the material in this area to essentially act like a low alloy steel, which is anodic to the chromium rich grains. Otherwise, preferential intergranular corrosion will occur parallel to the grain boundary, that is, eventually grain boundary will simply fall out. Design for intergranular corrosion. How to minimize, how to prevent intergranular attack. Watch welding of stainless steels, which causes sensitization in stainless steels. Always needs proper annealing after welding to redistribute chromium. Use low carbon grade stainless steels to eliminate sensitization. For example, 304L and 316L. Here L stands for low carbon. Add alloy stabilizers like titanium, niobium, or otherwise columbium and tantalum, which ties up with the carbon atoms and prevents chromium depletion. The forthcoming 7 slides throw more light on the intergranular corrosion behavior, that is intergranular attack, in a more metallurgical manner, in a more technical manner. Intergranular corrosion, shortly called IGC, is a form of localized corrosion characterized by preferential corrosion at grain boundaries or the areas adjacent to them, with little or negligible attack on the grains. Similarly to other forms of localized corrosion, it mainly occurs on the passive alloys such as aluminum and stainless alloys, exposed to specific corrodants, specific corroding environments. Like other common materials, metals have a visible grain structure when they are viewed under magnification. Rapid corrosive attack of immediately adjacent grain boundaries with little or no attack of the grains is called intergranular corrosion. Rapid attack at the grain boundaries can result in grains dropping or falling out of the metal surface, resulting in the disintegration of the steel. Figure 1 on the left side shows the appearance of surface where intergranular attack is occurring on the grain boundaries. In practical application, the loss of cross-section thickness and the introduction of cracks can have severe consequences for applications like pressure containment. With austenitic stainless steels, intergranular attack is usually the result of chromium carbide precipitation, that is Cr23 and C6 at grain boundaries, which produces a narrow zone of chromium depletion at the grain boundary. This condition is termed sensitization. It is pictorially shown in figure 2. on the left hand side. You can see here the yellow round is chromium carbide, the light blue round is chromium ions, and black round is chromium and carbon. You can see along the grain boundaries chromium depleted zone, where on the grain boundary you can see chromium carbide, yellow rounds are there. Because the chromium is primary alloying element of stainless alloys that makes stainless steel corrosion resistant, the chromium depleted regions are susceptible to preferential corrosion attack. In term it is called intergranular attack. It is believed that this occurs because the chromium content immediately adjacent to the carbide may be below the required for the stainless alloy to resist corrosion. If the carbides form a continuous network on the grain boundary, then corrosion can produce a separation or gap at the grain boundary and possible grain dropping or loss. 3 approaches have been used with the austenitic stainless steels to minimize the effects of intergranular attack. Chromium carbides tend to precipitate at the grain boundaries of the austenitic stainless steels in the temperature range 950 to 1450 Fahrenheit. Any exposure or thermal excursion into this temperature range during metal manufacture, fabrication, or welding or any other service could potentially sensitize the steel. Common practices such as welding, stress relief, and hot forming can expose the steel to the sensitizing temperature range. The formation of chromium carbides is readily reversed by a solution annealed heat treatment. The test methods outlined in ASTM A262 have been developed to detect susceptibility to intergranular attack in austenitic stainless steels. The time and temperature required to produce susceptibility to intergranular attack, shortly called IGA, is dependent on alloy composition, particularly the carbon content. Figure 3 above shows the time temperature sensitization curves for type 304 stainless alloys with varying amounts of carbon content. 3 approaches have been used with austenitic stainless steels to minimize the effects of intergranular attack. Materials that has been sensitized can be solution annealed by heating to a temperature where carbides dissolved and the chromium depleted regions are eliminated. The carbon is then kept in solution by rapid cooling through the sensitizing temperature range. The recommended solution anneal temperature depends on the alloy and is typically done in the temperature range of 1900 to 2150 degree Fahrenheit, followed by rapid cooling. Resistance to intergranular attack can also be achieved by reducing the carbon content to below 0.03% level. The figure the top shows low carbon contents less than 0.03%. Move the nose of the time temperature sensitization curve to longer times. That is, if you see below 0.03, you can see it ranges between 10 hours, 100 hours and 1000 hours, longer times. The low carbon grades such as types 304L, 316L and 317L have been designed to resist sensitization during typical welding operations, but they do not resist sensitization by long-term exposure in the critical temperature range in service. On the contrary, the higher alloyed, more corrosion-resistant stainless steels such as 904L and 6 molybdenum alloys have very low carbon contents, and the susceptibility to intergranular corrosion attack is typically not a concern. The addition of stabilizing elements such as titanium, niobium or columbium and tantalum can also provide increased resistance to sensitization. especially for long-term exposures in the critical range and service. These stabilizing elements tend to form carbides that are more stable than chromium carbide in the temperature range 2250 to 1450 degree Fahrenheit. So as the alloy cools from high temperatures, the carbon combines with the stabilizing elements and is unavailable for chromium carbide precipitation at lower sensitizing temperature range 950 to 1450 degree Fahrenheit. Common stabilized austenitic grades include type 321, 347, 20 Serbium 3 and 316 titanium. Above figure shows the carbide precipitation reactions that occur in type 304 and 347 stainless steels. Temperature range precipitation reactions at the melting point nearly about 2250 degree Fahrenheit. The precipitation reactions are niobium or columbium carbide dissolves and chromium carbide dissolves. At the temperature range of 2250 to 1450 degree Fahrenheit, the precipitation reactions of columbium carbide precipitates and chromium carbides dissolves. At the temperature range 1450 to 950 degree Fahrenheit, the precipitation reaction is chromium carbide precipitates. At the temperature range 950 to 70 degree Fahrenheit, the precipitation reaction is no reaction. With the stabilized grades, standard solution annealing treatments generally do not tie up all the available carbon. So in the stabilized grades in the solution annealed condition have long time exposure to the sensitizing temperature range, that is 1450 to 950 degree Fahrenheit. Chromium carbide precipitation and sensitization can occur. Stabilizing heat treatments can be used to more effectively tie up carbon by completing the precipitation reactions. These treatments consist of holding the alloy for several hours in the temperature range 1500 to 1600 degree Fahrenheit. Intergranular attack of ferritic stainless steels. Although intergranular attack of ferritic stainless steels is similar to that found in austenitic stainless steels, there are some important differences. Because the solubility of nitrogen is low in the ferritic crystal structure, the precipitates that cause sensitization in ferritic grades include both chromium carbide Cr23C6 and chromium nitrides Cr2N. With the ferritic grades, sensitization occurs during cooling from higher temperatures, that is greater than 1700 degree Fahrenheit. At these high temperatures, the carbides and nitrides are put into solution, and during cooling they can precipitate at grain boundaries, resulting in chromium depletion. The very high diffusion rates in the ferritic structure make it impossible to cool the steel fast enough to avoid precipitation of carbides and nitrides at grain boundaries. For this reason, most commercial ferritic grades avoid sensitization by restricting the level of carbon and nitrogen and requiring the addition of stabilizing elements such as titanium, tantalum and niobium. If sensitization has occurred in a ferritic stainless steel, the condition can be healed by back diffusing chromium into the depleted regions. Healing can be achieved by holding the material at the temperature range 1100 to 1200 degree Fahrenheit for several hours. The figure schematically shows the healing, how to achieve healing of austenitic stainless steels for several hours. The test methods outlined in ASTM A763 have been developed to detect susceptibility to intergranular attack in ferritic stainless steels. Thank you very much for watching this video.